Hi, my name is Orion Ning, and today I'd like to talk about my work with Chris Desert, V. Hong, and Ben Safdi on search for axions from magnetic white dwarfs with Chandra. First, I'd like to talk about the lore behind searching for axion signatures from magnetic white dwarfs. Our work builds upon the well-established fact that axions can be thermally produced through electron bremsstrahlung in a degenerate white dwarf core, shown in the center of this figure, and which usually reaches core temperatures on the order of a keV to a few keV. The axions then stream out of the white dwarf and convert to X-ray photons in the magnetosphere surrounding the star, which for magnetic white dwarfs can be very efficient, given their typical field strengths on the order of hundreds of megagauss. This is why we search for magnetic white dwarfs in particular. The optimal instrument for searching for these axion-induced X-rays then would be the Chandra telescope. Now, this type of search has been done before, in particular through previous work by Desert et al., finding no evidence of axions from the magnetic white dwarf REJ0317, inferring strong upper limits on the axion-electron axion-photon coupling combination of around 1.3 times 10 to the minus 25 inverse GeV. In this work, we strive to probe this coupling combination with the same mechanisms, although this time we use dedicated Chandra observations of two new nearby magnetic white dwarfs which have the potential to be highly sensitive to this type of axion emission given their relatively high core temperatures and magnetic fields. These two magnetic white dwarfs, which we observe in 2022 and 2023, are PG0945 and WD1859, which we'll refer to as PG and WD respectively. PG is a carbon-oxygen magnetic white dwarf with a core temperature of around 1.5 keV and magnetic field strength of around 670 megagauss, whereas WD is an oxygen-neon magnetic white dwarf with core temperature of around 2.2 keV and magnetic field strength of around 800 megagauss. Interestingly, WD is an example of an ultramassive white dwarf with mass greater than around 1.3 solar masses, making it particularly rare and unique amongst white dwarfs. Here we show the spatial maps of these white dwarfs within the Chandra ROI, and remark that for WD we are only showing here bins greater than 3 keV with no observed counts near the source, although we did observe counts below this, which we'll discuss later. Consequently, we don't analyze bins below 3 keV for WD. So ultimately, we analyze the Chandra data of these two magnetic white dwarfs in bins from 1 to 9 keV, and show here the energy spectrum of both the data, which is consistent with 0, as well as an example axion-induced signal. Given the non-observation of axion-induced signals, we can set 95% upper limits on GAEE times GAGG at the level of 1.54 times 10 to the minus 25 and 3.54 times 10 to the minus 25 inverse GeV for PG and WD respectively at low axion masses. Displayed here also are expected limits and 1 and 2 sigma containment intervals for the upper limit. We note that our analysis here gives comparable sensitivity relative to the previous analysis for REJ, and is amongst the most competitive in this displayed region of parameter space. However, one can wonder why we ended up with weaker sensitivity than what one would expect given the ideal astrophysical properties of these magnetic white dwarfs. There are a couple of important reasons to take away. One is that we actually discovered excess emission between 1 to 3 keV for our observation of WD, shown here in this low keV spatial map where there's clear emission near the star's location. However, this emission is too soft to be explained by axions. It might actually be non-thermal emission in the magnetosphere, as analyzed in another work. Nonetheless, that means we have to exclude this bin from our analysis, giving us weaker sensitivity overall. The other important point we discovered is that there appears to be instrumental degradation of the Chandra instrument itself, manifesting in particular as significant decreases in the effective area over the past couple of years, shown here. This then significantly impacts our expected sensitivity in this analysis. Here we show that, were it not for these effects, the limits from PG and WD on GAEE times GAGG would be notably stronger, and in most of the mass range would surpass the previous limits from REJ, shown here as dotted lines compared to the fiducial bolded lines. These are all important effects to consider in similar future searches with Chandra. Despite still ending up with competitive sensitivity, our work suggests that Chandra's degradation limits its utility for similar magnetic white dwarf axion searches. One can look forward, however, to exciting similar future instruments, such as the proposed Lynx X-ray Observatory or the upcoming Athena telescope, which would greatly improve sensitivity to the axion couplings discussed in this work, given their much larger effective areas. Another promising approach would be the search for axion production in populations of white dwarfs or other relevant stars in, for example, nearby galaxies, which are likely to have even higher sensitivity to axion emission than that considered from just isolated single stars. In conclusion, despite various effects significantly affecting our sensitivity, we pushed the limits of axion searches with Chandra in this work with two new magnetic white dwarfs, and still are able to infer competitive sensitivity compared to current leading constraints on axion parameters. And we look forward to other exciting avenues of improving axion coupling sensitivity with future instruments and astrophysical approaches. Thanks for listening, and we hope you check out our paper.